In this next section, let's take a look at what are called Cauchy-Euler equations. So far, we've seen situations in which we solve both homogeneous and non-homogeneous nth-order linear ODEs. But so far, we've been restricted in that our coefficients have to be constants. In general, a non-constant set of coefficients requires a very different set of concepts. However, there is one specific case where even though we don't have constant coefficients, we still have a nice closed form answer to our problems. Okay, so here we begin with a definition. Let's take a set of real numbers, a sub 0, a sub 1, all the way up to a sub n, be real numbers. And let's have g be a function that is continuous at least on the interval from 0 to infinity. Then the equation a sub n, x to the n, nth derivative of y, plus a sub n minus 1, x to the n minus 1, n minus first derivative of y, plus plus a sub 2, x squared, second derivative of y, plus a sub 1, x to the first power, first derivative of y, plus a sub 0 of y, or not of y, times y, is equal to g of x. This is a Cauchy-Euler equation. Before we get into examples of this and how to solve this, we do have a quick little note here. You may remember from chapter 4, at the beginning of chapter 4, we had some theorems of existence, some theorems of if our functions follow certain criteria, then we're guaranteed to have a unique solution. One of those conditions was that the leading coefficient could not be 0. Now, of course, up until now, that hasn't been an issue because so far our leading coefficient's always either been 1 or some number that we divide away to make this 1. So either way, our coefficient's always been a constant. And those constants, well, they're constants. They're not 0. They are whatever value they're assigned. But here, this can be 0 if x equals to 0. So since a sub n x to the n is equal to 0 whenever x equals to 0, then by our theorems of existence in chapter 4, we can only guarantee a unique solution if we exclude x equals to 0. So that means that we have the choice. We can either solve for all values from 0 to infinity or from negative infinity to 0. And we generally make the choice of all values from 0 to infinity. So we can only guarantee a unique solution if we exclude x equals to 0. That means we will look for solutions on the interval from 0 to infinity. So here we only consider solutions on the interval from 0 to infinity. If there are any solutions that are defined outside of that interval, that's fine, but we don't care about those. We only care about solutions that are defined here at the minimum. All right, so let's see here. Okay, so here we are going to solve this in a way that's I guess first of all we should see an example of this, yeah? Okay, so let's say something like this. Let's do x cubed y triple prime minus 3x squared y double prime plus 6xy prime minus 6y is equal to 3 plus the natural log of x cubed. Okay. All right, so a couple things to note. First of all, look at the pattern of a Cauchy-Euler equation. Your coefficients are not constants anymore, but they're not completely arbitrary either. They're not completely random. the coefficient is going to be a monomial term whose power matches the number of the derivative taken at that term. So here, if you have y triple prime, the coefficient has to be a third degree monomial, 1x to the third. Here, second derivative, this is a second derivative monomial, 3x squared. First order, 6x to the first power. No derivative, okay, no variable here, just a number. So you're going to have a number times x to a power. That's going to be your coefficient. So it's not just a number anymore. They're not constants, but they're numbers times x to a power, and the power matches the number of the derivative of that term. Third derivative, third power, second derivative, second power, first derivative, first power, no derivative, no variable. Also notice here that we are not taking any steps backwards. We're not saying, oh, well, now that we have a different kind of coefficient, we better play it safe and have this function here, the input function, be a polynomial or a sine or an exponential. No. We're still considering the possibility that this might be something completely arbitrary. It might be a logarithm, it might be an inverse trig function, a hyperbolic function, or anything else. So variation of parameters may still be necessary for these problems. Okay, so how are we going to solve these? We're going to be using a characteristic equation, an auxiliary equation, to find, we're going to find solutions to that characteristic equation, and we're going to stitch those together in a certain way to find our solution. You say, well, that's exactly what we did when we had constant coefficients, so what's the difference? The difference is that our auxiliary function is a little different now. So here, I will come back to this example. I'll be solving this one, but first let's write out the technique. Okay, so technique. This is to solve a Cauchy Euler equation. Okay. All right, so first of all, we're going to solve the associated homogeneous problem using a substitution. Solve the associated homogeneous ODE. Now, here, you might say, well, is there just a characteristic equation that I can memorize? I mean, I kind of did that with the constant coefficients. The answer is yes, there is just a auxiliary equation you can memorize. However, those are going to depend on the degree of your ODE. So unlike when we had constant coefficients where we said, oh, well, we're just going to write it like if it were a polynomial and factor, here, exactly what your characteristic equation looks like doesn't just depend on how many terms you have, it depends on the power. So this would have one kind of characteristic equation, whereas adding one more term doesn't just add one more term to the characteristic equation, it adds a bunch of other stuff as well. So although there are some formulas that you can memorize, there's a lot of them, and it's really not worth the time. Instead, we're going to have one simple technique that will work regardless of what powers you have or what order you have. Here we're going to solve the associated homogeneous ODE using the following substitution. And it's a very simple one. Using the substitution, y equals x to the m. You might wonder, okay, so wait, what's m? Is it, so like if it's a third order problem, do I use x to the third? No. You leave it as x to the m. You'll see that when we start doing the problem, but here m is going to give us our characteristic equation. It's not an accident that we're using m. It's the same kind of notation we used in previous characteristic equations. Okay, so we're going to use the substitution x to the m and then solving to get y sub c. Exactly what y sub c you get depends on what the solutions to your characteristic equation are. Let's see. If you're, how do I want to write that? Let's just say it this way. If you have distinct real roots, you're going to have, let's say, m1, which is not equal to m2, which is not equal to m3, which is not equal to ... Then you get, then your fundamental solution set is going to be x to the m1 So no, this is not exponential anymore. These are monomial, x to a power. X to the m2, x to the m3, dot, dot, dot. On the other hand, what if you have real roots, but they're repeated? With a repeated real root, things that look like m1 is equal to, is not equal to, is equal to. You get used to writing is not equal to on these. Is equal to m2, is equal to m3, is equal to dot, dot, dot. Then your fundamental solution set is going to be, the very first one, you're going to write it as if it were a unique solution. You're going to write that as x to the m1. But then the next one is going to be that same x to the m1 times the natural log of x. The next one will be that same x to the m1 times the natural log of x quantity squared. The next one will be x to the m1 times the natural log of x quantity cubed, and so forth. A quick little warning here. A lot of people will say, well, natural log of x squared, I can take the 2 and bring it down, right? No. That's when the power's on the x. Here, you're not squaring the x. You're squaring the whole thing. The 2 can't be brought down. That stays up there. Okay, so be very careful. That's a common mistake with this one. And then, let's see, I've got distinct real roots, repeated roots. And then what happens if I have complex roots? So I have distinct complex roots, the kind that are going to look like a plus ib and a minus ib, a plus ib and a minus ib. Then our fundamental solution set that's going to be given by x to the power of a, where again a is the real part, times cosine of b times the natural log of x, where b is the imaginary part. And then the other element of your fundamental solution set will be the exact same thing, but with sine instead of cosine. So x to the a sine of b natural log of x, like that. Okay, so that is how we solve for the homogeneous ODE. And then the next step is going to be to solve the particular solution. Find the particular solution. And here we're going to be using variation of parameters. And finally, as always, our general solution is just going to be y equals our y sub c found up here in the first big step here, and then plus our particular solution found here in the second step by variation of parameters. And that will give us our solution to a Cauchy Euler equation. Okay, so let's go ahead and give that a try. I'm going to go ahead and use the same one that I had earlier. I'm going to just rewrite it so I don't have to keep flipping back and forth. All right, let's see. So example, let's go ahead and solve. Oh, I've already forgotten what it was. I don't want to flip back and forth, but I have to flip back at least once. X to the third, y triple prime, minus 3x squared y double prime, plus 6xy prime, minus 6y equals 3 plus the natural log of x cubed, like that. As I mentioned earlier here, natural log of x squared, natural log of x cubed. This square is the whole thing. You can't bring that down. Here, this cube is not on the whole thing. This 3 can be brought down. And in fact, I think I'm going to want to do that in a little bit. But anyway, for now, I'm going to write it exactly as it was written before. But yeah, this one I can bring down, because that one is cubing just the x. All right, but in any event, let's go ahead and give this a try. So first of all, we're going to find our y sub c, and that is the solution to x cubed y triple prime minus 3x squared y double prime plus 6xy prime minus 6y equals to 0. And the way we're going to do that is by the substitution y equals x to the power of m. Okay, so this y is going to be replaced by x to the power of m. But what about all the rest of these? Well, those are just derivatives. This is a monomial term. You can easily take derivatives. Just use the power rule. That's why I said the substitution is going to be way easier than any formula you could ever memorize. You're just going to use the power rule a couple times here. So here I'm going to take the m, bring it down, minus 1 from the power. Again, taking a second derivative. Well, I've already brought the m down, so now I bring down m minus 1. So m times m minus 1, x to the m minus 2. And then for my third derivative, I'm going to have, I already brought down my m. I already brought down my m minus 1. So next I'm bringing down my m minus 2, x to the m minus 3. Okay. And I'll just plug those all in. So this is going to be x to the third, y triple prime, that's going to be m times m minus 1 times m minus 2, x to the m minus 3, minus 3x squared times my y double prime, that's m minus 1 x to the m minus 2, plus 6x times my y prime, that's m x to the m minus 1, and then finally minus 6 times my y, which is x to the m. Study that for a moment and consider that there's a common factor everywhere. It's x to the m. Notice right here, this is x to the m. You say, yeah, but that's the only one. There's no other x to the m's. Sure there are. Every single term has one. Because if I take x to the m minus 1 and multiply by x is like saying x to the first power. When you multiply two things that have the same base, you add their powers. So here this 1 cancels that minus 1, and you get x to the m. Here this 2 cancels that minus 2, and you get x to the m. This 3 cancels that minus 3, and you get x to the m. Every single one of these has a common factor of x to the m. So let me factor that out. If I factor out x to the m, that gets rid of this and this. That gets rid of this and this. That gets rid of this and this. And that gets rid of this there. So all that's left is m times m minus 1 times m minus 2 minus 3m times m minus 1 plus 6m minus 6 equals 0. Okay. Okay, so now we can clean this up. Oh, let's see, that's x to the m times, let's see, if I multiply all this out together here, I've got m to the third. That's going to be minus 3m squared. And then plus 2m. And then over here I've got minus 3m squared plus 3m plus 6m minus 6 equals 0. Here I've got x to the m times m cubed minus 3 minus another 3, that'll be minus 6m squared. That'll give me 5 and 6, that makes 11m. And then minus 6 equals 0. All right, so through this substitution, we get this equation. But notice that x to the m can never equal to 0, no matter what power m is, unless x itself is already 0. All right, if you have any number and raise it to a positive power or a negative power, you're going to make it bigger or smaller, but you won't get 0. If you do x to the 0, you get 1. So you can never make this 0 unless x itself is already 0. But we can't do that, remember? In order to guarantee a unique solution, we're going to exclude x ever equaling 0. So since that can never be 0, well, then it's got to be this that's 0. This is your auxiliary equation. So that means that our auxiliary equation here, our characteristic equation, is m cubed minus 6m squared plus 11m minus 6 equals 0. Once you do this a couple of times, you'll very quickly realize that every single time that's what's going to happen. The x to the m is going to cancel every single time. Or well, it's going to factor first and then cancel. So what you can really do is you can say, well, look, if I've got y here, I can just leave that off, right? I can just leave off the y. Here, where I've got y prime, I can take the 6x and multiply by an m, and then over here I can take the 3 and multiply by m times m minus 1. And then over here, I can take and multiply by m times m minus 1 times m minus 2. Notice the coefficients just stayed the same. That's 1, minus 3, 6, and minus 6. 1, minus 3, 6, and minus 6. Those numbers stayed the same. Oh, my finger's too thick. Let me try that again. 1, minus 3, 6, and minus 6. 1, minus 3, 6, and minus 6. And then here, nothing. Here, m. Here, m times m minus 1. Here, m times m minus 1 times m minus 2. If this was fourth order, guess what the next one would be? Just m times m minus 1 times m minus 2 times m minus 3. So can you memorize a bunch of these formulas? Sure, but you need a different one for each power. It's just easier to remember it this way. Either do the substitutions, and if you do the substitutions a few times, eventually you'll probably get this. Even if you're not trying to get this, you'll just kind of remember this form. Keep the numbers the same. First one, the one with the y has no m, and then from there it's m, and the next one is m times m minus 1. The next one is m minus 1, m minus 2. The next one would be m minus 1, m minus 2, m minus 3. And the x to the m part, all these x's factor out, and because of the restriction on the domain of this, they don't give you a solution. So this is the part that gives you your auxiliary equation. Okay, so now we can go ahead and solve this. We can solve this by factoring. Use your favorite factoring techniques here. One thing I noticed right away here is that the number 1 is a solution to this. 1 minus 6 is negative 5. Negative 5 plus 11, that's 6. 6 minus 6 is 0. So since 1 is a solution, m minus 1 is a factor. And if I take this and divide by m minus 1, 1 minus 6, 11 minus 6, and it'll give me, drop my 1. 1 times 1 is 1. Add those gives me negative 5. Negative 5, add those is 6. Negative 6, and that's 0. So if I divide that, I end up with m squared minus 5m plus 6. Use your favorite factoring technique, whatever applies, whatever works. Go ahead and factor. And then here I can factor this a little bit further. Or if I wanted to, I could use the quadratic formula, whatever. Again, this is just algebra. Use whatever you feel like as long as it works. So that's going to be m minus 2 and m minus 3. Oh, this problem works out as 1, 2, 3. Okay, that's nice. So here we end up with our 3 roots to our auxiliary equation. m1 is equal to 1, m2 is equal to 2, and m3 is equal to 3. Oh, that's a nice one. I just picked this one at random, and it worked out really nicely. Okay, so since we have distinct roots, none of them are equal to each other. Right? We have distinct real roots. Then our fundamental solution set would be x to the first power, x to the second power, and x to the third power. Right? That's my fundamental solution set. That's going to be x to the first power, x to the second power, and x to the third power, which means that our complementary solution is going to be c1 times the first one, plus c2 times the second, plus c3 times the third. So our y sub c is, let's see, c1x plus c2x squared plus c3x to the third. And so now all that's left, I say all that's left as if it were a short thing to do, is to find our particular solution, and that's by variation of parameters. So here we go. So now we're going to find our y sub p. We're going to find our Wronskian first, which we're going to take our fundamental solution set, write that along the top, x squared, x cubed. And then take the first derivative of all of those. That'll give me 1, 2x, and 3x squared. And then the derivative of all of those to give me 0, 2, and 6x. Taking that determinant, let's see, I'm going to get 12x cubed. I'm going to get 0, and I'm going to get 2x cubed. minus, I'm going to get 6x cubed. I'm going to get, oops, that's a cube. And then another 6x cubed. And then 0. And so I end up with 12 minus 12 cancels out, and I just get 2x cubed. So my Wronskian is 2x cubed. And then I'm going to find my W1, my W2, and my W3. W1, replace the first column with all zeros, except at the very bottom, go ahead and put your input function. 3 plus, what I'm going to do here is I'm going to take this 3 and pull it out. There's a property of logarithms that says if you have an argument with a power, that power can be brought out as a coefficient. I'm not sure, but I strongly believe that if I pull that out, it's going to make my computations easier. If not, I can always put it back in there. But I'm going to write this as 3 plus 3 log of x. 3 plus 3 log of x. And then the other two columns remain the same. X squared, 2x2, x cubed, 3x squared, and 6x, like that. And so my determinant is going to be 0 plus, let's see, I've got 3x to the 4th times 3. That'll be 9x to the 4th plus 9x to the 4th log of x. Okay. And then the third one is 0, like that, minus, and then going back the other way, I've got 0, 0, and 6x to the 4th plus 6x to the 4th natural log of x. So here 9 of those minus 6 of those will give me 3 of those. So W1 is 3x to the 4th plus 3x to the 4th natural log of x. That's my W1. Okay, let's see. My W2, take my x, my 1, and my 0. Now replace the middle column with 0, 0, 3 plus 3 natural log of x. And the last column, x to the 3rd, 3x squared, 6x. And that would give us, let's see. I've got 0, 0, and so just this one. 0 plus 0 plus 3x to the 3rd plus 3x to the 3rd natural log of x minus, and then going back the other way, I've got 3, that'll give me 9, x to the 3rd plus 9x to the 3rd log of x, and then 0 and 0. So then 3 of these minus 9 of these will give me negative 6x to the 3rd minus 6x to the 3rd natural log of x. Like that. Okay, and then I've got my W3. So I've got, take the first and second column from my Wronskian, leave those alone. x1, 0, x squared, 2x, and 2. And then replace the third column now with 0, 0, and 3 plus 3 natural log of x. And that would give us, let's see, 2x squared times 3, that'll be 6x squared plus 6x squared log of x plus 0 minus, and then going back the other way, I've got 0, I've got 3x squared plus 3x squared natural log of x, and then 0. So 6 of those minus 3 of those will give me 3 of those. I get 3x squared plus 3x squared natural log of x. Okay, now we're going to go ahead and take these and divide by our Wronskian to get our integrands for u1, u2, and u3. So for u1, I'm going to take w1 right here, and I'm going to divide it by w. So here, let's see, I've got 3x to the 4th plus 3x to the fourth natural log of x. And we're dividing that by 2x to the third. And we're going to integrate that with respect to x. Okay? We'll come back for the other ones. Here, the x to the third divides into both of those. 3/2 is a common factor. So I'll pull the 3/2 out, leaving me the integral of just x plus x natural log of x. Dx like that. Oh, you know what? I've just realized I made a mistake here. Yes, I've just realized I made a mistake here. It's not hard to fix, but I've made a mistake here. In order to solve for the particular solution using variation of parameters, this has to be in standard form. Okay, so that doesn't affect anything about the complementary solution. This is perfectly fine. But in order to use variation of parameters, I do need my problem to be in standard form. Standard form means this should be 1. So before I proceed, I should divide everything by x to the third. Like that. So that doesn't change anything here. Down here, all it changes is that my, let's see. I need to divide this by x to the third. That doesn't appear at all on the Wronskian, but it does appear here, x to the third. It appears here, x to the third, and it appears here, x to the third. So that doesn't change anything other than the fact that all of these are divided by x to the third. I got kind of lucky there. I made a mistake that is easily corrected. I wish I could say I did that on purpose. Oh yeah, I did that on purpose to show you all that you're supposed to put this in standard form, otherwise you get an error. No, that was a mistake. I forgot to do that. Okay, so now that I've got this in standard form up here, then these are now the correct W1, W2, and W3. So let's see. Okay, so then that means that W1, all of these x to the fourths should have been divided by x to the third at the beginning. So the numerator itself should just be 3x plus 3x natural log of x. And then that's being divided by your Wronskian, the 2x to the third. Okay, so there we go. All right, so then the 3/2 is a common factor, which I will factor out. And then, let's see. And then when I divide, I guess I don't have to write that out. I can just write it underneath here. So 3/2 is the common factor. When I factor out the 3/2, I'm left with x plus x natural log of x. And on the bottom, I've got x to the third, like that, over x to the third. And then these x's cancel one of those x's. So my u1 is going to be 3/2, the integral of 1 plus natural log of x over x squared. All right, there we go. That is not correct. Okay, so now we can integrate that. Okay. Likewise, we can have our u2, and that's going to be the integral of, you're going to take your w2, which, okay, let's see, here's my w2. Well, here the x to the third in the denominator cancels all these x to the thirds. So we just get minus 6 natural log of x. But then we have to divide that by our Wronskian, which is 2x to the third dx. Like that. And, well, here 6 divided by 2 is 3, so we can just factor that out. In fact, they both have a negative, so I'll factor that out as well. So I get minus 3 integral of 1, well, there's not really anything else, right? Just 1 plus natural log of x over x cubed dx. And then my u3 is going to be the integral of, I'm going to take my w3. Okay, so w3 is here. I'm going to have this x to the 3 is going to divide these away, and I'm going to still have a single x on the bottom. So I have 3 plus 3 natural log of x over x, like that. But then I have to divide that by our Wronskian, by our 2x cubed. So that 2x cubed will come down here with this x, giving me 2x to the fourth dx, like that. Okay. And all of these have, well, I can pull out the common factor, 3/2 integral, and that's really about it. There's nothing else to do there. X to the fourth dx. All of these are doable by integration by parts. And since this problem's already gone on pretty long, I'm going to go ahead and just tell you what the result is here. So if I integrate this by parts, I get, so I need a negative there. So I end up with negative 3 halves natural log of x plus 2 over x. That's my u1. If I integrate this by parts, I end up with, that'll be 4. So I'll end up with negative of a negative. That'll be positive 3/4 2 times the natural log of x, or you can say natural log of x squared, it's fine too, plus 3 over x squared. Again, all these should have a plus c, but we set them all to 0 each time, so we don't need to worry about that. And then for this one, I would have, let's say I need to have a negative, and then that'll be 12. So that'll be, yeah. So that'll give me negative 1/6 e natural log. So it'd be negative 1/6 times 3 natural log of x plus 4 over x cubed. Yeah, and you could write this as x cubed here as well, or leave it as 3 natural log of x. Either one's fine. So these are our u1, u2, and u3. And so now we can go ahead and get our particular solution. Y sub p is going to equal to, you're going to take your u1 y1 plus u2 times y2 plus u3 times y3. So let's see, that'll give me negative 3 halves natural log of x plus 2 over x times, and then our y1 was, what was our y1? Our y1 was x. Going back to the complementary solution, we had x, x squared, and x cubed. So we're going to take our u1, multiply times x, and that one's nice because you just cancel that. And then our u2, that's going to be 3 plus 3/4 times 2 natural log of x plus 3 over x squared. And that's going to be, oh, that one also cancels, x squared. That's nice. And then plus negative 1/6 3 natural log of x plus 4 over x to the third. And then that's multiplied by our y3, which is x to the third for this problem. And so those cancel. And then you can just combine your like terms now. So let's see, I've got, what have I got? Negative 3, because the 2's cancel. And then here I've got 9/4, and then minus 4/6, which is the same as saying minus 2/3. So that is, oh, let's see, that's common denominator is 12. So negative 17/12. I think that's right, yeah, negative 17/12. And then for my logarithms, I've got negative 3 halves plus 3/4 times 2 the log of x minus a 1/6 times 3 the log of x. So that's negative half, that's 3 halves, and that's minus 3 halves. So I just end up with minus half the natural log of x, which is a little unexpected. That's kind of a small answer, but it is what it is. So in the end, our solution, thus our general solution, is y equals y sub c plus y sub p, where our y sub c was found early on to be c1x c2x squared plus c3x cubed. Plus our particular solution, which since that's a minus, I'll just write minus there. So that'll be minus 17/12 minus 1/2 the natural log of x. And this would be our general solution to this Cauchy Euler equation here, which makes us happy. All right, so that is it for this section. Note that the technique here for solving the homogeneous version is the new part. This right here is an example of just variation of parameters. I figured it'd be a good example of one just to see it and use in different contexts. But this stuff is stuff we've already seen previously. This is the new part, which is honestly not that bad. Here you use the substitution y equals x to the power of m. You don't solve for m here. You use it as m. Take derivatives using the power rule and substitute in. That gives you your auxiliary equation, which is then solved for m1, m2, m3, however many you have, and that gives you your fundamental solution set, which you can then stitch together to form your complementary solution. Right. So that is it for this section. That is it for this topic. If there's any questions, comments, or problems, please let me know. And I hope you all have a nice day.